Welcome to example number 7. So it's similar to the last problem with the ladder leaning against a wall, but in this case we have a bucket that is tied to the ladder. And we're asked to figure out what would be the coefficient of friction between the ladder and the floor. Alright, so what is basically the coefficient of static friction is what we're looking for. Now we're told that this bucket has a mass of 1 kilogram. So I'll just call that maybe m sub 1, which is 1 kilogram. And we're told that the ladder has a length of 3 meters, but has a mass, we'll write that as mass 2, which is 4 kilograms. And the bucket is 2 meters from the base of the wall. So the remains stable from it. Now I'm just going to try to interpret that. I'm assuming that this is 2 meters along here, not 2 meters along this x-axis. Well, maybe I'll just label this as 2 meters here and this is 1 meter there. Okay, so then let's draw a free body diagram for this ladder. Okay, I just drew the body separately here so it's a little bit less cluttered. So at the wall, we have a normal force from the wall. I'll label that as N sub W. Then about 1 meter from the top end here, we have the bucket's weight, which I'm just going to label that as M1G. And at the geometric center of this, we have the weight of the ladder, which is a bit bigger. It's about 4 kilos. I'll label that as M2 times G. Then down here on the ground we have two forces. We have the perpendicular force, that's the normal force. That's probably going to be quite big actually because you can see these two downward forces. And I'll label that the N sub F, or the normal force from the floor. And then we have the horizontal force of friction. Welcome to example number 7. We're revisiting the slipping ladder, but a little bit of a different twist. We have now some weight tied in between the ladder here. So there's another additional vertical force. Plus, we're asked to find the coefficient of static friction in this case. Okay, so let's kind of label some information. We have the ladder is 3 meters long. I'm just going to label that here as 3 meters. It has a mass of 4 kilograms. So I'm just going to write the mass of the ladder. We'll write as M sub 1 is 4 kilograms. Then there's this paint bucket, which has a mass of 1 kilogram, and it is hanging 0.5 meters from the top end. So I'm assuming this from this distance is 0.5 meters. The ladder remains stable against a frictionless wall, so there's no friction here. And the bottom end is 2 meters from the base. So this distance from here, this is a right angle in here, is 2 meters. Okay, so my first part would be I would need to pick a body that's in equilibrium, which is the ladder. And I'm just going to draw the free body diagram separate, not to clutter up this picture here. Okay, there's our ladder. So let's draw all the forces that are acting externally on the ladder and show the forces at the points of application. So we have right here at the top end of the ladder, the wall is pushing on it. So there is a perpendicular force over here. I'm going to label that as N sub W for the normal force from the wall. Then we have this bucket that is pulling down. It has a mass of 1 kilogram and it's 0.5 meters away. So I'm going to draw that force, that little force right here. And now I'm going to show the other force. This is the weight of the ladder, which is acting at the center of gravity. And then let's look at the lower end of the ladder. At this point, there's going to be two forces. We have the upward normal force. It's going to be quite large, this force, because of the two forces that are going down here. I'm going to label this as the normal force due to the floor. And then we have the horizontal inward force here to balance out with the wall pushing outwards on here. And there's the force of friction. So now we're going to need to determine the coefficient of static friction. Now the coefficient of static friction is equal to the force of friction, divided by the normal force. So the force of friction, we know we have to find that over here. And the normal force, by the way, is the normal force from the floor, not from the wall, but from the floor. So we need to find these two forces, and if we can find those two forces, then we're in business. I like to always start with the sum of the forces personally, just because it's just easy to set up. So we choose an x and y axis. I'm going to choose an x axis to the right and a y axis straight up. And now I'm going to apply our sum of forces. So if I do the sum of the forces along our x axis, that will be equal to 0. And so the force, normal force from the wall minus the force of friction equals 0. So the normal force from the wall is equal to the force of friction. At this point, that doesn't really help me out because I don't know neither of those forces. Okay, what else? We'll just leave that as one equation here. Let's go along the y-axis. Sum of the forces along the y-axis equals 0. And we can see that the normal force from the floor minus these two weights, m1g and m2g, equals 0. So the normal force from the floor, we can find that out. That's just equal to the sum of these two weights, which is really just m1 plus m2 times g. So we can compute that now. That would be 5 kilograms. That's 4n1 times 9.8 meters per second squared, which gives you a normal force from the floor of 49 newtons. So we've got this part. Now we need to find the frictional force, or the normal force from the wall. So, well, it's really up to you. You now would need to apply a torque about some point. You either need to find this force or this force. It really doesn't matter to me. I'm going to just choose this point right here just because there's two forces there and I have 1, 2, 3 just to deal with. So we're going to do the sum of the torques about this axis of rotation, point P is equal to 0. And then we're going to have 1, 2, 3 different torques. So we have the normal force from the wall, which is going to cause it to rotate clockwise, which is a negative torque. So we have the negative torque from the wall. Then we have these two torques, which are going to cause it to go in the opposite rotation, which are counterclockwise. So those two torques are going to be positive torques. So we have the torque from, I'll just call that 1 for this weight, and we have the torque from this guy, number 2. And they all balance out to be 0. Okay, and now substituting in our magnitudes of our torques into here. So the torque from the normal force from the wall would be the force, which is the normal force, N sub W, multiplied by this position vector, R sub W, multiplied by the sine of the angle, theta. So theta is in here, and we don't know that yet. Theta is also down here, because these are alternate interior angles. And you can hopefully see that theta is over here in our triangle. Now you happen to know this length is 2 meters along the floor and 3 meters along the hypotenuse. So, and this is also a right angle, we're assuming we have a nice vertical wall. So you can actually figure out theta just using trigonometry. You see, if you know the adjacent side and the hypotenuse, you could use cosine of theta is the adjacent, which is 2, over the hypotenuse, which is 3. And so theta is the arc cosine of 2/3, which gives you an answer of 48.2 degrees. So you actually know this angle. And you know this distance here is going to be 3 meters. It's the length of the board from the point of axis to where that wall acts. Okay, moving on to the next torque. We have the torque produced by this bucket, which is going to be the weight of that bucket, which is m1 times g. Now, I'm just looking at my diagram, and I'm realizing that m1 is the lighter weight. So I'm going to make a difference over here in the answer, but m1 is actually, based on my picture, is this little bucket, and m2 is the beam. So there's a bit of a mix-up here. This should actually be 1 kilo, and this should be 4, based on the labeling of my diagram down below. Okay, so then we have now the torque produced by the bucket, which is m1 times g, that's the force from that bucket, multiplied by this distance here, we're going to call that just simply r sub 1, then multiplied by the sine of the angle. Now the angle is not going to be theta, it's this angle right in here, or this angle right in here, or this angle up here, which is, I'll just call that phi. So it's the angle sine of angle phi. Now, by the way, if you know this is a right triangle, this is 90 degrees, you know this angle down here is 48.2 degrees. You should be able to figure out that angle because that's just really 90 minus theta, which is basically 41.8 degrees. So phi we happen to know as well. Okay, now moving on to the beam's torque. So the light beam here, we have a mass of m2 times g times r sub 2, which is this distance from here to the axis of rotation toward x, then multiplied by the sine of the angle phi, same angle. And all of these torques add up to 0. It's good to write it all out in variables. I'm noticing that a lot of people tend to make mistakes here. They forget, for example, the distance r, or they just mislabel masses just like I did. There's a lot of little mistakes that people can easily make here. Okay, so the normal force in the wall multiplied by r sub w, which is the distance from the axis of rotation to where that force acts, which is the length of the ladder, which is 3 meters long. So it's 3 meters times the sine of the angle, which is 48.2 degrees. All right, next, the weight of the bucket, M1, is 1 kilogram. The acceleration due to gravity is 9.8 meters per second squared. And R1 is the distance from the axis of rotation to where that bucket acts. Now, this is 0.5 meters up here. So if this is all, 3 is all the way from here to here, that would make this distance from the bucket to the axis of rotation 2.5 meters. So we have 2.5 meters. And then multiplied by the sine of the angle up here, which is 41.8 degrees. Next, we have the torque from the beam. That's 4 kilograms times 9.8 meters per second squared. That's the force. Multiplied by the distance between the axis of rotation here to where this force acts, which is basically the middle of the beam. It's the geometric center where the center of gravity is because it's a uniform beam. And that's going to be half of this length, which is half of 3, which is 1.5 meters. And then this is then multiplied by the sine of 41.8. Okay, hopefully I haven't made any mistakes with all these substitutions. Now I'm ready just to solve for this unknown force here. Okay, 3 times sine of 48.2. By the way, the meters here, and the meters here all cancel out. So we're going to get negative NW times this, which is 2.236 approximately, plus this torque, and all of this multiplied is going to give you 16.3 repeating, and plus this, which will give you 39.2, and all of this equals 0. Adding these together, you're going to get 55.5, and then divided by 2.236, you'll get the normal force from the wall is 24.8 newtons. Okay, we're almost in business now. So we need to find the coefficient of static friction, which is given by this formula. We now know the normal force from the floor, which is 49 newtons. I also know the normal force from the wall, which is 24.8 newtons. And because the horizontal forces balance out each other, then the normal force of the wall is equivalent to the force of friction, so the force of friction is equal to 24.8 newtons as well. So to find the coefficient of static friction, we just take the ratio of the force of friction divided by the normal force from the floor. So the force of friction is 24.8, and the normal force from the floor is 49. These are both in newtons. And this will give you a coefficient of static friction of 0.507. And there's your answer.